In the history of military engineering, there is a fine line between brilliant innovation and impractical megalomania. No weapon crosses this line as forcefully as the Heavy Gustav, known in German as Schwerer Gustav. This was not just a cannon, it was a railway supergun designed to fire projectiles with a diameter of 800 millimeters. We are not talking about the length of the weapon, but the width of the firing tunnel itself. A machine so massive that it required its own railway infrastructure to move and a small army just to operate. Designed to destroy the indestructible, the Gustav was the physical manifestation of the Third Reich's obsession with so-called Wunderwaffen, the wonder weapons. But to understand this machine, we must ignore the myth and focus on the metal, the ballistics, and the strategy that justified the construction of the largest gun ever used in combat in human history. To comprehend the existence of the Schwerer Gustav, it is necessary to go back to the mid-1930s. Nazi Germany was rearming, challenging the restrictions imposed after World War I. However, the Wehrmacht High Command faced a formidable geographic and architectural obstacle on its western border, the famous Maginot Line. France had built a series of static fortifications considered impenetrable. These were reinforced concrete bunkers of colossal thickness, connected by underground tunnels and defended by heavy artillery. The German military doctrine of the time, which would evolve into the well-known Lightning War, or Blitzkrieg, relied on speed and movement. However, fortifications like the Maginot Line could halt the German advance, forcing a static war of attrition, something Hitler wanted to avoid at all costs. The military problem was clear. Germany needed a tool capable of punching through 7 meters of reinforced concrete or 1 meter of solid steel armor, all from a safe distance, outside the range of French retaliatory artillery. In 1934, the Army High Command issued an order to the Krupp family, the steel dynasty responsible for Germany's armament for generations. The technical requirement was brutal. They needed a cannon capable of firing a projectile heavy enough to destroy the deepest fortifications of the Maginot Line. Gustav Krupp took on the challenge personally. Initial calculations by ballistic engineers indicated that to achieve the necessary penetration with a single impact, the projectile would need a caliber of around 800 millimeters and weigh 7 tons. To fire such mass at supersonic speed, the cannon itself would have proportions never seen before. No road could support it. No tracked vehicle could carry it. The only viable logistical solution was the railway. Thus was born the concept of the ultimate railway gun. The project was approved, and the race against time began to have it ready before the invasion of France. The strategic irony is that the machine was delayed. When the Wehrmacht invaded France in 1940, they simply bypassed the Maginot Line through the Ardennes forests. The Gustav was not ready, and its reason for existing had vanished. However, the invasion of the Soviet Union in 1941, with Operation Barbarossa, presented new targets. The fortress cities of Crimea needed to be taken, and the bunker buster would finally have a purpose. The Schwerer Gustav was not comparable to a tank or a standard field howitzer. In terms of engineering, it was closer to a naval destroyer placed on rails. The technical specifications of this machine demonstrate the peak of German metallurgy and, simultaneously, the logistical nightmare it represented. The complete gun weighed 1,350 tons. To put that in perspective, this is equivalent to the weight of approximately 25 heavy tanks combined, or more than 1,000 modern cars stacked together. The heart of the weapon was its barrel. With a length of 32.5 meters, the rifled tube had a caliber of 80 centimeters. Most naval guns on the largest battleships of the era, such as the Bismarck or the Japanese Yamato, possessed calibers between 380 and 460 millimeters. The Gustav had nearly double that diameter. To withstand the violent recoil of a shot of this caliber, the weapon's chassis could not use a standard railway line. The weight would crush the ties and the recoil would derail the train. The Krupp engineering solution was to distribute the load. The Gustav was mounted on 2 parallel sets of tracks. The chassis was supported by 4 large bogie wagons, totaling 80 wheels, to distribute the colossal weight. The operation of the weapon required 2 main types of ammunition, each being a masterpiece of destructive ballistics. The first type was the concrete-piercing ammunition, technically called betongranate. This projectile weighed 7 tons and 100 kilograms. It was a hardened chrome-nickel-steel cylinder designed not to explode on impact, but to penetrate kinetically before detonating. The second type was the high-explosive ammunition, the Sprenggranit. It was slightly lighter, weighing 4 tons and 800 kilograms, designed to create massive craters and lethal shockwaves in open areas. The maximum range was 47 kilometers for the lighter projectile and about 38 kilometers for the armor-piercing one. The firing mechanics were complex. The cannon did not possess horizontal rotation on the chassis itself. To aim left or right, engineers needed to build a specific curved railway track at the firing site. The weapon was moved forward or backward along this curve to adjust the horizontal direction. Only the barrel elevation, which could reach 48 degrees, was adjusted on the machine itself to define the range. The loading process was slow and methodical. The barrel needed to be lowered to a horizontal position for every shot. A dedicated crane at the rear of the weapon hoisted the massive projectile. After the projectile was inserted, the gunners inserted the propellant charge. This was not a single piece, but rather several bags of smokeless powder, the quantity of which varied according to the distance of the target. The combustion chamber was closed, the barrel raised, and the shot fired electrically. This entire operation generated absurd thermal and mechanical wear. The internal lining of the barrel had an estimated lifespan of only 48 to 100 shots before needing replacement, as the friction of 7 tons of steel deformed the barrel's rifling with every shot. Theory and tests at the Rügenwalder proving grounds proved the weapon worked. But the reality of combat is very different. The true test of the Schwerer Gustav occurred in June 1942, during the Siege of Sevastopol on the Crimean Peninsula. Sevastopol was the most fortified city in the world at that moment. The Soviets had transformed the port into an impenetrable citadel, protected by armored coastal batteries and underground forts. It was the exact scenario for which the Gustav had been conceived. Moving the weapon from Germany to Crimea was a logistical operation of industrial scale. The cannon traveled disassembled on special trains. To assemble and operate it, General Erich von Manstein, commander of the 11th Army, allocated an impressive workforce. About 1,500 men were needed just to lay the tracks and prepare the firing positions. Another 1,000 men formed the artillery battalion responsible for direct operation. Furthermore, 2 anti-aircraft defense battalions were assigned exclusively to protect the Gustav from air attacks, as the weapon was a static and vulnerable target. In total, almost 4,000 people were involved in the operation of a single gun. Assembly took weeks. On June 5, 1942, the Gustav fired its first shot in combat. The targets were the Soviet coastal batteries, known by the names Fort Stalin, Lenin, and Molotov. The impact was devastating. Unlike aerial bombardments that spread damage on the surface, the Gustav's 7-ton projectile carried unstoppable kinetic energy. The most notable shot, which validated the entire engineering project, occurred against the ammunition depot at Severnaya Bay, a location nicknamed White Cliff. The Soviets had built this depot 30 meters below the sea floor, protected by natural rock and layers of reinforced concrete. They considered it invulnerable to any existing conventional weapon. The Gustav fired 9 piercing projectiles against this position. One of the projectiles traversed 30 meters of bay water, pierced the rocky seabed, broke through the submerged bunker's concrete, and detonated inside the ammunition magazine. The resulting explosion was registered as an artificial earthquake. The depot was obliterated instantly. In another attack against Fort Stalin, the projectiles simply disintegrated the concrete casemates. The morale of the Soviet troops inside the fortifications was broken not just by the physical destruction, but by the terrifying sound of the incoming projectile. Reports describe a high-pitched hiss that resembled a freight train falling from the sky. During the Siege of Sevastopol, the Gustav fired 48 projectiles. The original barrel already showed severe wear by the end of the battle. From a purely tactical point of view, the weapon was an absolute success, as it destroyed targets that no other German weapon could scratch. Despite the technical success in Sevastopol, the victory was tactical, but the strategic defeat of the weapon was already drawn. The Schwerer Gustav was an anomaly in a modern war. The limitations were glaring and insurmountable. First, there was the problem of mobility. To move the weapon, 25 freight trains were needed just for components, tracks, and personnel. Assembly on site took 3 to 6 weeks. This meant the Gustav could only be used in static, prolonged sieges. In a war that changed rapidly, like the Eastern Front, the enemy could simply retreat or maneuver before the weapon was ready to fire. Second, aerial vulnerability. The Gustav was a gigantic target. It required total air supremacy over the firing region. If a single enemy bomber spotted the position, the largest cannon in the world could be turned into scrap metal in seconds. This demanded massive Air Force resources for protection, resources that were desperately needed on other fronts. Third, the rate of fire. In ideal conditions, the Gustav could fire about 14 times a day. Compared to squadrons of Stuka dive bombers, which could deliver tons of explosives with precision in minutes and return to refuel, the cost-benefit ratio of the Gustav was terrible. After the fall of Sevastopol, the cannon was taken north to the Siege of Leningrad. It was assembled but never fired. The Soviet army launched an offensive that forced the Germans to retreat before the weapon could be used. From then on, the Gustav became a burden in the German retreat. The weapon was moved back to Germany, and later, with the collapse of the Reich imminent, engineers received the final order to destroy the equipment. In April 1945, American troops found the wreckage of the Schwerer Gustav scattered in a forest in Bavaria. Its twin brother, the cannon known as Dora, which saw even less use, was also found destroyed. The Germans had detonated the breech blocks and barrels to prevent the technology from falling into Allied hands. What remained was sent to the foundry. The largest cannon in history did not end up in a museum, but as scrap. The Schwerer Gustav was the apex of railway artillery, and at the same time, proof of its obsolescence. It proved that German engineering could build anything, but failed to ask if it should. It functioned exactly as designed, a technical marvel capable of destroying mountains, but unable to change the course of a war that no longer depended on size, but on agility, logistics, and air power. It remains in history as the steel dinosaur of World War II. Formidable, terrifying, and hopelessly doomed to extinction,